this is Mrs. Murdock, and this is a lecture on osmosis and tonicities. What does tonicity mean? Well, there's 3 states of gradient that can exist between 2 different solutions, and we call them, you may remember this from freshman year, hypertonic, isotonic, hypotonic. Hopefully that rings some bells. So let's look at each one in turn. So let's say we have 3 beakers, and the 3 beakers each have some water in them. And they also have, let's say they have a giant red blood cell, nice and big so we can really see that there is a difference between the water outside the cell and the water inside the cell. And let's say that in this first situation, the inside of the cell has a, let's say a salt molarity of 0.3. And in fact, all of the cells, since they're the same type of cell, the molarity inside the cell is 0.3 molar. And let's say that we're talking about salt. Okay, so remember that whenever we're talking about water movement, right, in a situation where water is flowing down a gradient, where diffusion is happening, or where osmosis is happening, there isn't just one solution in this beaker. There are 2 solutions. One inside the cell and one outside the cell. All 3 beakers have that situation where there are 2 different solutions and the solution concentrations can be different, creating, if they're different, creating a gradient. Okay? So let's say that in this first one, the outside water is 0.8 molar salt. Let's say over here the outside solution is 0.3 molar. And over here the outside solution is pure water, no salt in it at all. Okay, so if you heard me talking about gradients, the gradients amongst these 3 beakers exist here. There's a gradient here because there's a difference across this membrane. There's more salt, if I make little dots indicating salt, there's more salt molecules floating around outside this cell than there are inside the cell, right? So that creates a gradient because there is a difference in concentration. So maybe inside, fewer salt molecules, but a lot out here. Over here, there isn't a gradient. There's no gradient at all because the concentration both outside and inside the cell is the same. So maybe out here we've got some salt molecules like that, and in here about the same, right? So there's no gradient here. The third situation over here, we do have a gradient because there's no salt in the solution outside the cell, and there is some salt in here, right? Okay, so now let's do some definitions, and maybe this will sound familiar. In terms of the solutions that we are defining, in this situation, we're going to be only talking about the outside solution, the solutions out here. But that doesn't mean that the solution inside the cell can't be called one of the tonicities as well. Right? In this situation, this outer solution here is hypertonic. Hypertonic, I'm spelling that, right? Hypertonic to the solution inside the cell. And hypertonic, what hypertonic means, I'm going to bring this up a little bit. Hypertonic means more concentrated than the solution it's being compared to. In this case, the solution inside the cell. Right? So hyper, that should make sense to you. Hyper means more. Hyper means more. Okay. More salt out here, less salt in there. The middle beaker since the concentrations are the same, we call that isotonic. Isotonic, which means same concentration. As the solution it is compared to. Okay. And then the final one over here, since this is less concentrated, we call that hypotonic. Hypo, right? As opposed to hyper, hypotonic. This is less concentrated. Okay, I'm just going to move my picture over here for a second. Okay. Less concentrated then. Solution it's compared to. Can everyone read my handwriting all right? Just give me a thumbs up. All right. There. Okay. Give you a minute to write that. All right, so now I'm going to go for blue for this. Now, this is really about osmosis. Let's only think about this in terms of water movement. Because usually it's water that moves fastest in these situations because of the many aquaporins in all of the cell membranes. Water tends to be the thing that's going to move first. So if I look at, since I'm over here, and we're starting over here, which way is the water going to move in the hypotonic situation? In. Very good. Now what is the logic with that? Water moves in because in every situation, diffusion is going to happen so as to reach equilibrium. So water will move in because that will help the salt molecules inside the cell to become more diffuse and better become equal with what's outside the cell. Will it ever reach equilibrium? Probably not, because you have absolutely no salt outside the cell. So this cell, and in fact most animal cells in a hypotonic solution, will eventually burst because you can't ever reach equilibrium. So that's what would happen. In this situation, water moves in. To allow equilibrium, right? But since this almost can't ever reach equilibrium, but fate of an animal cell, since it doesn't have a cell wall, right? Someone has a question. It's okay. Ask.
I can't read the second one.
Oh, okay. I'll get back to that in just a minute. I'll be moving over.
The second, dash.
Is that better? The fate of the animal cells is to burst in this situation, right? Because in this situation, you'll never reach equilibrium, right? Okay, so in a hypotonic solution, most animal cells are going to swell, and if the difference is too great, they'll often burst. Okay, now let's go to the isotonic situation. All right, in the isotonic situation, what's going to be the water movement? What do you think? There won't be any net movement, right? So no net movement of water, but you will have something called dynamic equilibrium, where the water will move both ways equally. And for animal cells, that's ideal. It's called dynamic equilibrium. And animal cells are happiest that way. So, happy animal cells. All right, so just to reiterate, isotonic means same concentration as the solution it's compared to. In an isotonic solution, there's no net movement of water, even though it moves equally both ways, and that's called dynamic equilibrium. Animal cells prefer that situation most. How many of you guys have ever had an IV hooked up to you? Or had a friend or family member? Yeah, me too. Okay, so there are quality control people who make sure that the fluids that go in those IV bags are exactly the same concentration as human blood plasma. And that's really important because you don't want to be putting fresh water into somebody's arm. You'll damage their blood cells if you put too much in there. Or really, really too salty water because you get the other problem, which we'll talk about now. Okay, so let's go to hypertonic. Now which way is the water going to flow? Out, exactly. Okay. So now kind of think about, okay, all right, just that. All right, so now you have the water flowing out, right? A net flow out. Water flows out to reach equilibrium, right? And the fate of the cell, cells shrink. They dehydrate. Animal cells don't like that. Hypertonic situations are really bad. In fact, not just for animal cells. There are very few cells. Most cells don't like this, whether animal or plant. Really, really salty water situations are bad news most of the time, except for specialized plants. Like if you've heard of the mangroves that live along the coast of Florida, and there's a lot of mangrove trees that live around the ocean, they're actually specially adapted to live in salt water. There aren't very many plants that can do that. If you give really salty water into someone's IV, you'll be causing their cells to dehydrate. And cells don't do very well when they dehydrate. Not very happy. Okay. So that is osmosis and tonicities. And I hope that was helpful.